Hello, everyone. Welcome to this session. My name is Wycliffe, and today I want us to learn how to obtain long-term climate data for your region of interest. You may be conducting your study in some location. For example, you want to do a project in this tea growing region of Kericho, or you want to do your project in the east of Rift Valley in this tea growing region, or you are outside Kenya and you are conducting your tea research in maybe Rwanda, or you are doing your research on tea in another country like Ethiopia, or any other country of where you are interested in doing some research. It doesn't have to be tea. You could be conducting your research in some arid environment, or even in Sri Lanka, or whichever country or whichever region of interest you are interested in. In most cases, it's important that you show climatic variables, or somebody will be asking you, what is the long-term rainfall in this region, or what is the mean rainfall in this region, or if you want to establish your experimental plots in more than one location, it may be important to know or to present information regarding long-term climatic variables like rainfall or temperature or something. Say you want to compare tea production in the east of Rift Valley and west of Rift Valley in some locations, then you might be interested in obtaining this climatic data. In most cases, these data are very difficult to obtain if you want to go through the process of writing letters or emails to some departments, asking them to give you monthly data or annual data for a long time period. Somebody could be on leave and you wait for 1 year or several months. Somebody could just not give the data or tell you you have to pay or something like that. Well, there is this Idaho Terra Climate monthly dataset, which has monthly data for most of the climatic variables you might be interested in from 1958 to date. So for example, in the bands, you can see there is evapotranspiration data, there is climate water deficit, drought severity index, precipitation, about soil moisture, maximum temperature, minimum temperature, vapor pressure, there is wind speed at 10 meters height, vapor pressure deficit, among other variables. So these variables, you can actually get them annually or monthly from 1958 to date for almost any location globally. So that's what we are trying to do today. Okay, so let's get to the Colab. I prefer working in the Colab environment. Make sure you name your Colab, your Python notebook correctly, so that it is not untitled 0, untitled 1, untitled 2000, untitled 10,827. Yeah. Okay, so we start by importing necessary libraries. For now, we will just import, let me zoom in a bit, Earth Engine and GMap. I know we will also we will also load another package called matplotlib, but that is coming later. Okay, so after importing this, we authenticate our repository and our credentials, and then we initialize the project. So in initializing the project, we need to provide the project name. And my project name, I can get it from the Google Earth Engine. Here, I go to my project info, and this is my cloud project. Okay, so I copy that and I bring it to my project, and then that's all. So normally it will ask me to accept some options. So if you see that, just accept, continue, and then it will be fine. Once you see that tick, then we can create a map of our region of interest, or we can show the GE map itself with base map of, say, satellite. This is safer, easier, and faster than writing letters, knowing somebody in some office to give you the data, begging, writing email, visiting, burning fuel in the road to go to someone who will actually process the files for you and send you the data. This is way easier. So once we call the map, we can draw a region of interest. For now, I'm interested in this tea growing region of Kenya. And then you can drag a region of interest. Previously, in my previous videos, I showed you how you can import your shapefile as, or your GeoJSON as a GE and then use it. So, but if you just want to set up some experiment here, or you need some rainfall data, annual rainfall data, or something like that for this kind of region, you just drag a region of interest. Sizable. We can delete this, clear all, and draw another one which is even smaller. If you just want a smaller region like this, or just some experimental plot somewhere, you just drag a smaller one. Okay, so let me get back to a bigger one. Because, for example, if you want to do an experiment here, then it's an experiment which will be affecting tree growers or tea farmers in the whole of this region. So it's better you capture that in your data. Okay, so the region of interest itself will become, from the map which we have drawn, we pick the last feature. So draw last feature. And then this last feature, we are only interested in its geometry, that is its coordinates. So that gives us a polygon with 5 coordinates, and the 5th coordinate is the same as the first coordinate if you look at the numbers here and the numbers here, because that's when the line is closed and we call it a polygon. Okay, so after getting your region of interest, now we call our data, which is the Idaho. I will use this Idaho Terra climate. This part, which is the documentation or description, it's important for you to read it so that you know the kind of data you're working with. Again, it's important for you to know that the resolution is about 4.6 kilometers. That means if you want to compare regions that are smaller than 5 kilometers apart, then the differences may not be captured. So take that into consideration when using this kind of data. Okay, so we will pick its snippet. Then I close this. Once I've picked the snippet, then I can say my CHAPS data, or you can even call it rainfall data. It doesn't matter. Is given by a tuple of whatever the snippet we have captured. And then, as I said, in this data, we have several bands. And for this, we are interested in precipitation. So this is the rainfall. So the precipitation band is just called PR. So we can select PR from that data set. So that means we are only using the precipitation. If you wanted another band, maybe minimum temperature, you will pick a different one like TMMN, I think. Yeah, this one for minimum temperature, TMMX for maximum temperature. If you want the average of the two, then you can also run that kind of analysis. So we will take this data, filter date. So we'll filter it for date. Let's say we want it as long as is available. So let's say 1958 from the first month until last year. So I'm making this video in 2025. So we want to pick it up to the last month of last year. Okay, and then we can check our rainfall data. So what are we seeing here? We are seeing an image collection of 804 elements. So why 804? 1958 minus, okay, 2024 minus 1958, we get around 67, 66, 67 years, because it's 66 plus 1. So 67 years times 12 months, because it's a monthly data, gives us 804 images, right? So we have a pile of 804 images. Then once we have the images, then we don't, for this case, we just want to summarize the monthly data. So I'm going to use we are going to use the annual data. So I'm not going to work with the monthly. So we can create a function. Okay, we can create something which help us to add each year all the monthly rainfall received. For example, if we say the start year, we convert to date, everything from year, month, day, like that. From the year, let's say 2024, January 1st, that is the start year. So the end year, that is the end of that period which we want to aggregate around, is the start year, but we increase that start year by 1. Yeah. And we are running this in the year, on the year. So that means if start is January 1st, then end is January 1st, but of the next year. So we have captured the whole of that year period. Okay. Then our image, which we are returning, is therefore the RF, which we already defined up here as our image collection. And in that image collection, we filter for the period between start and end. And the starts and end is the every year. Let's simplify it to every year. And then what we do with those images for each year is that we sum them so that we get the total rainfall received in that location for that year. So what are we returning after that sum? We return the image, but then we can set the year. We can give it an attribute called the year, which picks the year itself. So if it is 1984, it will be the sum of 1984. If it is 1985, 85, 80, 56, 90, 2001, then each image will carry that year with it. Okay, so that's just a definition of our function to run through the years. But then what are the years? So our years is a list. So we create an Earth Engine list, which is a sequence between 1958 to 2024. Yeah. So you can print the years and see how it looks like. So it's just a list from 1958 to 2024. So it's just a list of those numbers which we want to loop through in the definition or the defined function we have up there, right? Then what therefore is our annual rainfall? So with our years, we can map. Here, when we are applying a function on a list of objects, we use map function. So we map our function, which is the annual sum. And what we are returning here, we need to wrap it into an image collection. So that gives us annual, and we can check what annual is. And we now see that annual is 67 elements. So they are now not 804 because we have run this for each year. We've picked the first, we've summed for each year. And what we get is an image with a property called year, which we set up here to carry for us the year of each image. That is 1958. If you go to the next one, you see 1959 until the last one, which is 2024. Not that one, but the 66th one, which is the 67th, because it starts from 0. Cool. So we have all the images of annual images of the rainfall data which we want. Okay, so we want something which will give us a feature collection or something which we can pass to a data frame for our region of interest. So what we want to do is we can define another function. This, again, I'm still repeating that it's easier than knocking 1,000 doors. We can define a function. I'm wondering why the indentation there. Okay, so we can define our function and then we say the mean rainfall, because we've summed the rainfall for each period, for each year. But now to get the average rainfall received here, we now don't use the sum, which we applied here. Where did we define the function? Not there, not, yeah, here. We are now not summing them because we've summed for the months to form a year, but now we get the average for this, our region of interest. So we can call it mean for that. We take the image, each image that is for each year, then we reduce region because we just have one feature in the, to work with, not feature collection. What we call our reducer, like what we want to use to bring all those values within the region of interest together, is a reducer we call mean. So that's the mean function we are going to apply on the image, on each image, within a specific location, which is defined by geometry, and it is the region of interest. So that bounding box with 5 coordinates we defined earlier. And when it comes to scale, here it's important that you know the scale where you are going to operate within. Our region of interest is small, and just the resolution here is just fine. So we can go by the scale provided by the data itself, right? If we apply that, what we want to get is called precipitation, and in our function it's called PR. In the data set it's called PR, and then we return something after getting that precipitation. So we'll call it a feature because now we want to end up with a feature collection. That's a collection of so many features. We are not interested in the geometry, but we are interested in a dictionary which will contain maybe rainfall, not really here, but first of all, we get the rainfall in millimeters. So what is that rainfall in millimeters? That is the mean rainfall over that region. And then we also are interested in returning the year. And the year we added as a feature, as a property to each image, and we can get it using get function. This basically ends our function. So the function will take each image and reduce it for the region of interest at the native scale, and then pick precipitation and convert it to a feature. And we return it the feature, which is the rainfall plus the year in which that rainfall refers. Okay, so that's just a defined function. Now apply the function on your image collection. So we can call it rainfall. To apply it, we will call the annual rainfall. How did we define it? Yeah, we called it annual. Our collection is called annual. So on our annual, we map, sorry for those maybe relatively bad names, we map the function. The function is get mean rainfall. Again, this is way, way simpler than writing an email to 100 people, waiting, getting feedback like the person you are contacting is on holiday and will be back in office after 20 weeks or whatever. So in the feature collection which we have extracted, you can see now we have rainfall. For example, in 1958, this region received 1,824 millimeters of rainfall. In which year is this? In 2022, it received 1,550. In 2024, the region received 1,977 millimeters. So we have the data we want. Now, to make this data more user-friendly or bring it to a data frame, we can call it a rainfall data frame, and then that one we just use GMap. Yeah, somebody somewhere had thought of this and made it simpler for us to Earth Engine to data frame. For us, created a function which can help us to bring all this feature collection down to a data frame. So we pass our rainfall there, and then we can maybe inspect rainfall DF, maybe the head of it. Yeah, we see this error. I think must be a feature collection. So we can wrap this into a feature collection. Sorry for that. We can wrap this rainfall into a feature collection, and then that should work. Perfect. So we have the years, 1958 all the way, and we have rainfall for each year corresponding to it. Basically finished, but as I told you earlier, we may need to visualize this. Seeing is believing, so we can import matplotlib. So we can say import matplotlib is just a function which helps us to visualize. It's just a package or a library. Import matplotlib. Again, many people have been thinking about visualizing the data they have. Matplotlib, the data they have, and the way they visualize it is matplotlib.pyplot as plt. Yeah. And the way they visualize it is basically the same as what we will do. Data is data. So if it is rainfall and year, it is temperature and year, it is humidity and relative humidity and year, potential evapotranspiration and year, vapor pressure deficit and year, whatever it is, it's data. Whether it's sepal length, petal width, height of groundnut or whatever, and year, it's data. So the way we visualize it is basically the same. Okay, so with our PLT, our matplotlib pyplot defined or imported as PLT, we can create a figure. So we create a figure and we can define the size of our figure using fig size, and we provide a tuple of maybe 10 by 5. And then we can do the plotting, which is plt.plot. And what we plot here is rain, how did we call it? Rainfall DF is rainfall underscore DF. And that rainfall underscore DF, we pick what we call year. And that will be on the x-axis. And on the y-axis, we will have that rainfall DF. And then we pick rain in millimeters. That is this attribute here. We defined it here. When we were creating the feature, we fed rainfall to rain in millimeters. So that's the column name. And then we can provide, what else? We can provide, maybe we make it simpler without all these definitions. Or yeah, okay. Let's give it maybe just color as which color is normally used for maybe something bluish, like steel blue can be good with this. This plot will give us normally a scatter plot, but in this case, probably it's preferable to use a bar plot when you are talking about rainfall. Okay, so with that, we have our rainfall over time. Maybe something, this is totally up to your liking. You can add a title and say something like annual rainfall, uh, rainfall in Kericho, or something like long-term annual rainfall. If you want, you can add a title. The title has been added. Currently, we don't have any label on the X and the Y axis, so you can add those plt.x label. That function, you just provide what you want the label to be. What did I do? That puts year, and then you can also label the Y axis. Some of the things that don't need to take my time to explain or to visualize. And then it's important again to provide the units for the rainfall. So you can say annual rainfall, I think. That's better. So that somebody knows, okay, this is not daily rainfall or monthly, but annual. And then after that, we can maybe, I don't know, add grid if you want it to look a bit like easy to interpret. Like now we can't tell what is the value on each bar, but if we add a grid with some line type being line style, sorry, not line type, but line style being maybe dash dash. So we don't have block line, and then we give them some transparency of maybe 0.6, and then only on the y-axis. We give it y-axis. Yeah, so we see those lines. We don't need both y and x-axis, so we just see the lines on the y-axis, which tells us, which is easier now to interpret. For example, you know where 15 is, whether it's above or below, or just some slight adjustment. And then their layout is okay, but we can still go with PLT tight layout. Anyway, the copilot or the assistant there is also doing some good job. And then we end with plt.show. Okay, so that concludes just the visualization. So we have here, we know it's annual rainfall in millimeters, and we know it's long-term, actually from 1958 all the way to 2024. We know how much rainfall was received in that location every year. Somebody might say, I need this data now locally. I want to see it in maybe CSV or something like that locally. So you just say rainfall DF, which you have created, and then to CSV. I don't know if this is more difficult than writing thousands of email. So we call that rainfall, or Kericho rainfall, or something like that. Depends. Kericho rainfall .csv. You can call it long-term rainfall. I mean, that's super long name, but yeah. Okay, so if you run that, you have the data here, Kericho long-term rainfall, and you can left click. Okay, you can click these three dots and then click download. If you do that, it will be downloaded. Now you have it locally and you can open it as a CSV, and you now see rainfall, annual rainfall since 1958 for your region of interest, if you want to share with your colleagues, your professor, and anybody. Well, as I said, it doesn't have to be Kericho. You can change your region of interest and pick a region in Rwanda. Let's say you are researching on tea cultivation in Rwanda. I know these are tea fields in Rwanda. So you just drag within your region of interest. I don't know which region of interest you may be. Okay, maybe we make it a bit bigger for Rwanda. Okay, Rwanda like that. So that's a tea growing region in Rwanda. Then you draw the last feature as a feature collection. You import the Terra climate data for that region. Then you define your annual that already defined, the years as a list of 67 years, get annual rainfall function, get the rainfall itself, and then see the top, the first few. So you can see the values here are a bit different from what we were receiving the other side. Then we've imported that, you just visualize it. Everything remains the same. This is now data for Rwanda, tea growing region in Rwanda. Lastly, it doesn't have to be a tea growing region. Let's go to a desert. So I just clear all, and I hope this is a desert. So, and fingers crossed. I don't know whether we will have some rainfall in Sahara Desert. So we get our data, we define the annual function, we run the years list. We don't need to run most of this. Again, we only needed to run where we are applying it on the feature collection. Oh, I'm seeing some millimeters. Okay, so there has been some, anyway, yeah, and there are some years when there was some notable, but just 80. So this quite arid region, we've seen some rainfall. Well, lastly, that was lastly again, second lastly, we can go outside Africa. I mentioned Sri Lanka at some point, and I know there is tea growing region. It's somewhere in the mountains of Sri Lanka here. Where is tea in Sri Lanka? Okay, it doesn't have to be tea. That's a good one. Okay, it doesn't have to be tea. Let's just pick some region here in Sri Lanka as our region of interest. Then we draw the ROI. Here we don't need to rerun that. We don't need to rerun that. Here. That's a function. Map annual sum. That's also not, reducer. Here is where we need to apply the region of interest. And then we get our rainfall in Sri Lanka, annual rainfall in Sri Lanka. We didn't have to bring that. We can now see the rainfall in that Sri Lanka, way higher than what we were seeing in Kenya in terms of the thousands here. So probably that region in Sri Lanka is receiving more rainfall than. Yeah, then again, you can write it to CSV. You can save it as CSV. Sri-Lanka. Then you just click that and it goes to your folders here. Sri Lanka is here, 3 dots, download, and then you have your Sri Lanka data downloaded. Well, next time I will run a related study, but now when we have more than one location. For example, this one, we are just looking at one location. When we are in Kenya, we are just picking one location. But now we want to say, if you want to establish an experiment in more than one region, and you need this long-term temperature or rainfall data, how do you go about that? Thank you for your attention.